compressor efficiency. So in general, the efficiency of the compressor is the ratio of the ideal work, which is the one that being calculated, and versus over or divided by the actual work, which is the actual we call this. And when you say that is actual, what is already being fabricated and already manufactured. So what will be the output work of that one versus to the calculated, which is on the design phase. So that is the in general the compressor's efficiency. Now for the mechanical efficiency, so we have the symbol here, small m with a lower script of m. So that will be the mechanical efficiency of the compressor. So it is the ratio of the indicated work of the compressor divided by the brake work of the compressor. Now if the compressor is driven by a steam or an internal combustion engine, the mechanical efficiency of the system is that would be the indicated work of the compressor divided by the indicated work of the driving engine. Now for the compression efficiency, so for the adiabatic compression efficiency, so we have the ratio of the adiabatic ideal work divided by the indicated work of the compressor. Now for the isothermal compression efficiency, so we have here your n, then we have your lower script of t, so that will be equal to the isothermal ideal work, then it is divided by the indicated work of the compressor. For the mechanical overall efficiency, we have the mechanical efficiency times your compression efficiency. Now for the adiabatic overall efficiency, so we have the mechanical efficiency of the compressor, so this one, then multiply by the NC. So the NC stands for the adiabatic compression efficiency, and it is equal to the indicated work, then it is divided by ratio of the brake work, and that will be multiplied to the adiabatic ideal work, the ratio all over by the work indicated. Now the adiabatic overall efficiency is equal now to the adiabatic ideal work all over by the work brake. Now for the isothermal overall efficiency, so we have this equation representations, so is equal to now to the mechanical efficiency, okay, then multiply by the isothermal compression efficiency, and it can be also expressed as the isothermal, so can be also expressed as the isothermal ideal work divided by the work brake. Now for the volumetric overall efficiency, so it is equal now to your mechanical efficiency of the compressor multiplied by the volumetric compression efficiency. And also it can be expressed as the polytropic ideal work divided by the work brake. Now try to remember this one, that when we say indicated work, so that is the work that is being done in the cylinder, working done by the work inside the cylinder of the compressor. Now the brake work or the shaft work, so that will be the work delivered at the shaft of the compressor system. So on the shaft work, so if we have your compressor here, example, no, so this is your compressor, Then you have your you have your shafting connecting to the electric motor. Okay. So your compressor here, your piston here, so that is connected to an electric motor. So the brake work, that will be the shaft that is in here connected by the compressor and the electric motor. So that is the work being delivered. Now for the adiabatic compression efficiency, so that will be the compression efficiency what is are mostly or commonly used, no? So the compression efficiency there will be mean of would be the mean of adiabatic compression efficiency. Sample problem, no? We have a two-cylinder single acting air compressor is directly coupled to an electric motor running at given RPM of this is 1000 revolution per minute. Now other data as follows. So the size of each cylinder is 150 mm by 200 mm, and the clearance volume, so we have your letter C, that will be 10%. So the 10% of the displacement. So the exponent n for both compression and re-expansion process, we have the value of 1.6. Now for the air constant, we have your K, which is equal to 1.4, and we have the air molecular mass, which is 29. So calculate the volume flow rate, okay, of air delivery in terms of the standard air for a delivery pressure of 8 times ambient pressure under ambient condition of 300 Kelvin and 1 bar. Now for letter B, so what will be the shaft power required in the if the mechanical efficiency is 81%. Okay, so for the solution, so let's draw the PB PB diagram, okay, so that we can plot easily what are the process, so we can identify the given there. So I have here your pressure and your volume, no? Now again, during the suction, so we have the following process from here going there. So we have your, this one will be your 0.1. Then for compression, starting from here going up, okay. So this will be now our polytropic compression, where our PB raised to, that which is given, that will be 1.6. So PBN, so that will be 1.6. So this is your constant. Now this will become our 0.2, compression at 0.2. Then for the delivery, so we have now this one going to 0.3. So discharging of that one. Then going back for the compression, sorry, for the suction stroke. So this will be our 0.4 here. Okay, so this is the 0.4. Now for the given of the problem, we have initially your P1 or P1 is equal now to 1 bar, okay, which is also equal to or equivalent to 100 kilopascal. Now um for other given, so we have the RPM, which is your so this will be your small n. So it will be 1000 revolution per minute. and also the size of each cylinder. So we have a given size of the cylinder. So that will be the diameter there. So that is 150 mm. Then for the stroke or the length of the stroke, so that will be 200. Okay, so that will be your L is 200 mm. Also, we have the given clearance, so that will be 10% of the displacement. So we have here 10%. Also, we have the value of your K, which is 1.4. Reviewing that, our P2 here, so P1, okay? So for our P2, so it is stated that the standard air for delivery, so when we say delivery, that will be the discharge of the compressor. So that is 8 times the ambient pressure. So our ambient pressure is 1 bar, so that will be 8 times. So we can write equation for the value of your P2 is equal now to 8 times your P1. Okay. Now, remembering that in our pivot diagram, this is our B1 starting from here, starting from your 0 of volume, then going to B1 to 0.1. Now, for our volume displaced is starting from 3 to 0.1. Then our B1 prime, so that will be from 0.4 to 0.1. Now, for the problem A, for the question number A, so we're looking at delivery in terms of standard air for delivery of pressure of 8 times. So the volume rate of air delivery in terms of standard air. So we're looking here, what we're looking here is the volume prime or volume B1 prime. Okay. So we're looking at for the point A, for the question A. So we're looking now what will be the B1 prime. Now we can uh, we from the arrangement, no, if we can still remember that from our volumetric efficiency, it is equal now to your B1 prime divided by the volume displaced, volume being displaced by the compressor. Now, our volume displacement BD, so that is equal to pi over 4 d squared, the diameter, times the length of the stroke of the piston. Then we have your N, or the number of RPM. So it depends if problem is single acting or double acting. But our problem here stated we have a 2-cylinder that is a single acting. Okay, 2 cylinders only and a single acting. Now for the given data, so we can compute your volume displays. So we can directly substitute, I think. So since we have the diameter given also in the problem, the length of stroke, and also your N, so we can compute now your volume displays. So our volume displays is equal to pi over 4, the diameter, so that will be 150 mm. So I'm going to convert that already to 0.15 to meters. That will be squared. So I'm gonna square this one. Then I'm gonna multiply it by the length of stroke. So that will be 0.2 meter. Then multiplying it by n. So usually our n, that will be your n is equal to your so that is equal to your small n, okay, multiply by 1. So since it is a single acting type, so we'll be using that one. Now, since the problem states that it is a twin cylinder, so we have two piston in a cylinder arrangements, 2 sets. So, but it is a single acting compressor. So, I'm gonna put here the RPM. So we have the given RPM of the system of the electric motor, that will be 1000. So this will be revolution per minute. Then for single acting, we're gonna put it as 1. But since it is a twin cylinder, so that will be 1, then multiply by 2, since it is a twin cylinder given to the problem. Sorry, two cylinder, not a twin, but it is almost the same. So it's a twin cylinder, or call it two cylinder. So from here, we can directly solve our volume displays. So we have the value of volume displays, which is now equal to 7.069. So that will be cubic meter per minute. Now from here, since we're looking for your B1 prime, so we can rewrite here the equation, which is now equal to volumetric efficiency times the volume displaced. Since we don't have the given values for your volumetric efficiency, so we need to compute that one. Since we don't know, we don't have the value, so but we can compute that one. Now our volumetric efficiency, we have your equation for volumetric efficiency. So that is equal now to 1 plus C, no? So that will be 1 plus C, okay, minus C times the ratio of pressure 2 over your pressure 1, which is raised to the power of 1 divided by N. Then we can substitute the value, that will be 1 plus the clearance. So we have 10%, so that will be 0.10 minus 0.10, then multiply by the ratio of pressure. So for the ratio of this one, okay, remembering that we have there your P1, your P2 is equal now to 8 times your P1. So since we can rewrite the value for P2, or the ratio of P2 or P1, so that will be P2 over your P1, which is now equal to 8. So we can directly substitute this one here. So that will be 8 times raised to the power of ratio of 1 divided by the value of your N, which is 1.6. So now we have the value of your volumetric efficiency using your calculator. So we have 0.7332. So for the volumetric efficiency. So since we have already given we have now the values for the unknowns in order for us to compute the B1 prime, so we can directly substitute the values here. So our B1 prime now is equal to volumetric efficiency times the volume displaced. So we have 0.7332 for the volumetric efficiency times the volume displaced, which is 7.069. So that will be cubic meter per minute. Okay, multiply that one. So we have the product of 5.1. Okay, this is 0.83. So this will be cubic meter per minute, or we can express this one also as 0.08864 in terms of cubic meter per second. Now for the letter B, the shaft work required. So if the mechanical efficiency is 81%, so for the we called it we called it mechanical efficiency. The mechanical efficiency, we have your equation, so that will be uh, indicated work divided by the work break or the shaft power. So since we're looking now, so what will be the shaft power, or let's say this will be, or this can be expressed as your indicated work. So that is work in the we call it work inside the cylinder, so divided by the work, so that we can win work of the shaft, or WS. So we can express, so this is equal now to the value of 81%, and this is now equal also to your work indicated, which is inside, no? So what will be the work inside the cylinder? So we have the equation, which is your N, no? Work by the cylinder and piston arrangement. So we have your B1 prime here divided by 1 minus N, then multiply by the ratio of your pressure, that will be P2 over your P1 raised to the power of N minus 1 over N, that will be 1. Okay, then it is divided by all over by the work of the shaft. Okay, so since the pressure one is available, B1 prime is also available. We already computed one. This is given, and we have the value of this one. This one is also given, so we can directly solve the work shaft. So here let's derive our equation to get the value of your work of shaft. Okay, so that will be equal to 0.81. So multiply, sorry, no. So to get that value, so that will be the work inside the cylinder that is being produced during compression divided by the 0.81. So let's try to substitute the values here. So we have your work of shaft. So we have your N, that will be 1.6. Okay, multiply by the pressure 1, that will be 100. So that will be 100 TPA. So that we're going to express in terms of Newton per square meter. Then we have the volume 1 prime. So I'm going to express it in terms of, we're going to use the cubic meter per second value. So 0.0864. So this will be cubic meter per second. Then it is divided by 1 minus the value of your N, that will be 1.6. Then multiply by the ratio of P1 over P2 to P2 over P1. So since we have already the value for that one, the ratio, so it will be 8, no? The ratio. Then it is raised to the exponent of 1.6 minus 1 divided by 1.6, and this is minus 1. Okay, then all over the equation is divided by 0.81. Now we have the value of work of the shaft, or so using your calculator. So this, the work of the compressor, or the indicated work that is happening inside the cylinder, piston in the cylinder arrangement. So we have the value of 27.21. So this is kilowatt. Now divided by the value of your mechanical efficiency. Okay, so our work of the shaft now is equal to 33 no 33.59. So this is kilowatt. Okay, so that will be the work of the shaft. So that is the work that is produced also by the call it the electric that is also the work that is needed by the or that will be required to produce by the electric motor in order to produce this type of system that you can discharge, which is 8 times the delivery of the ambient temperature, which is the 100 kilonewton per square meter. So 8 times of that one, so that will be 800 kilonewton per square meter. That will be the output of the compressor. Okay, so again, so taking a look at the overview of the solution here. Okay, so starting from here going there. Okay, so looking at the overview of our solution, so starting from here, so from a 2-cylinder single acting. Okay, so then to the final solution, so we have this one. Okay, so that's it.